send you to. All right, well, I'm gonna do this not in. Oh no, there it is. Okay, so I have just a few slides to stimulate discussion and then mostly to refer to if people have questions about the instrument. I'm not gonna spend a lot of time talking here. But and this is being recorded, right? So I don't need to take notes. I can go back and look later.
Yeah, it's recorded.
Yeah. Okay. Great. Yeah. Thank you. So this is this is a slide from yesterday, just giving an overview of CORSAIR. And I'll just give two brief slides from yesterday, and then I have a few questions, so hopefully stimulate discussion. But I'd like to see where it goes beyond those questions. So CORSAIR is for people who weren't in yesterday's talk. It's a balloon-based coronagraph and spectropolarimeter that we're building right now at Smithsonian at the Center for Astrophysics. It's going to fly a test flight in 2024, where we hope to work out a lot of the kinks. And then the ultimate goal is a flight or multiple flights, science flights from Antarctica, where we'll be above the atmosphere and in the polar vortex, so we can kind of circle the pole for up to a month. And we'll have 24/7 sun, so no day-night cycles. And so this is, I think that the coordination questions are going to be focused on the future Antarctic flight. So it's sort of open because the instrument and the proposal for that flight hasn't been done yet. The instrument is not going to be vastly different, but we do have some questions, which we have some options for refining the instrument based on user feedback. And so I guess most importantly, right now, CORSAIR focuses on the silicon 9 line at 3.93 microns. It measures the full polarization state. So our science questions from the proposal are, we can probe both magnetic and plasma questions with the same observations. We have full Stokes. In theory, we'll be getting full Stokes vectors for continuously. And so we can analyze those depending on what we want to probe. We can analyze the same data to look at the magnetic field, including hopefully the magnetic line of sight or the line of sight magnetic field strength, and as well as waves and flows. And then in the Antarctic flight, we have the other two science questions open to us, which are based on targets of opportunity, like active regions and CMEs. So just to sort of generate some discussion here, I came up with a few questions. We can add more to this. So just generally, what are some of the science use cases that we can probe with coordination with COMP? What are the time scales? So just to give you an idea of what the baseline for CORSAIR, it gets an exposure every 0.5 seconds, an instantaneous exposure. We have the wave plate rotating. That's our modulator. It's a rotating wave plate. It rotates once every 4 seconds. So we can produce an IQUV map across the corona every 4 seconds. And then we can stack those in different ways. If we want something like line of sight velocity, we can just stack maybe 8 of those images of eye. We should have enough SNR then to derive the Doppler shifts. If we need more, if we want, like, for instance, Stokes B, then we would be stacking more like an hour or more of those.
Can I just ask a question?
Yeah, sure.
So you have half-second exposure. Does that mean that it takes half a second for the thing to rotate? You get 4 and they end up with 4 seconds for a full rotation?
It takes half a second. The exposure time is related to the saturation, the predicted saturation of the camera, including all the backgrounds. So we believe that we can integrate, and you want it to be like a relatively small amount of rotation. So we're predicting that in half a second will be close to the full well of the.
I mean, is the thing continuously?
Yes, it's continuously rotating.
Okay.
And so I didn't mention that. There's going to be some smear that we have to take into account when we do the calibrations. Yeah. It doesn't stop at stare. We considered that, but this was simpler, and we thought it could be would be okay. Could be calibrated out. But that's to be seen. So we have increased temperature coverage if we include both of these instruments, because iron 13 is at 2 megakelvin, whereas silicon 9 is more at around 1 million Kelvin. So we could think about science that can be done there. One of the things we wrote in the original CORSAIR proposal for the future was that we could undertake some tomography studies potentially, and Max and Kramer was kind of the lead on this. But I don't know whether this is not my field at all, but I just wanted to throw it out there if there's anything that can be undertaken together. And then finally, I wonder if we'll have some of the same analysis tools. So if there are things that people would want to share or collaborate on or have the CORSAIR team develop that would also be useful for UCoMP, then, you know, we can talk about that. And then there's 3 questions that are kind of open for the instrument going forward for Antarctica. And I'd be interested to hear what the community thinks. So one is the preferred, Joan asked this yesterday about what time in the solar cycle do we want to, would we most prefer to observe? We don't have a whole lot we have some control over that, but not a ton. We can wait, but we probably don't want to, but we can always fly again as well. And so if there's interest in observing solar maximum in our first flight is during minimum, then we can go again. We originally, I'm wondering if there are how important are the use cases for other lines besides Silicon 9? Because this instrument was originally designed to access the iron 13 line pair and helium 1083 and also Silicon 10 at 1430 nanometers. And we descoped those because they required mechanisms to refocus and wasn't going to be done in time for the 2024 test flight, but we could potentially add those back, especially if it's really important for the science flight. And then finally, we have widely spaced slits right now because we don't have a narrow filter. And I'm wondering whether, how useful is that? We're gonna get a narrower filter for the Antarctic flight, but that's a tech development project. And so I'm kind of wondering if you guys have input on what the requirements would be for how closely the slits have to be spaced to be useful for comparisons to come. So anyway, I guess we can just talk about this. If you have questions about the instrument, I have backup slides that we can probe specific parameters, whatever.
I got one.
Yeah.
So actually in your measurements, you also can do linear polarization correction, LVRI,
Mhm.
right? And you're observing continuously for 30 days, right? You don't have the day night.
Yeah.
And your spatial resolution is significantly better than comp, right? If I got your 2
It's like 2 arcseconds.
is that your,
That's our pixel space.
That's your pixel
So it's
size,
a
so
little
it's
bit
really
worse. It's probably
4
double
second
that or
resolution.
5. Yeah.
Okay,
But it's
so,
like-
and comp is.
I think I'm similar to that. Oh, you can.
UCoMP has 3 arcsecond pixels.
Okay, so it's not a huge difference there, but the day night is big. The reason I'm saying is that, and I've got a movie somewhere I'll show you, but if you do the L over I maps as a Carrington map, and the problem is when you get the day night, it's really chunky because you have to interpolate. You
Mhm.
get 5 hours, you have to like deal with the other 19 hours, right? You get them when you look at them when you do like the forward modeling from PSI or something. You get these beautiful kind of fault line patterns. I've got some plots of this that you can do as a function of height. And they're related to what people do with the topological S things. You got null points, if they're,
Okay.
I feel like that's something that you might want to look at, and I can
Okay.
show you the movies of it if
That
you
sounds
want.
great,
I'll
yeah.
find them somewhere.
Okay.
So yeah, add LVRI. It's meaningful for this, I think.
Okay. Yes. Oops. Well, I'm not gonna add
Or
it.
what do you call it? Linear polarization degree, I guess is what you call it.
Degree of linear
Yeah.
processing. Yeah.
So I noticed that you don't have waves as kind of something to coordinate on. And I mean, because you've got slits and you're scanning to build up an image.
We're not scanning. Our
You're
slits are gonna be
scanning.
fixed because, well, at least so the goal is for the test flight, it's just a demonstration. The slits are fixed and we just get as much signal under one slit. For the science flight, we're hoping to have the slits closely enough spaced that we can kind of interpolate between them without, much of a gap. And so that we wouldn't have to scan them. But that's a question. If it's,
How close will they be spaced?
that's sort of a question of how narrow a filter we can get. So they could be spaced kind of around, I think, 30 arcseconds at the best filter, if that's kind of the narrowest filter we can get.
So
I think I did that.
suppose you can see waves as long as the coherence length is 30 arcseconds
Yeah.
or greater. Is that true? So when you see the coherence of wave propagation, how long is that? Will a wave, it's greater than 30.
What I'm thinking, I could just see and I can tell you correctly. Slide.
Number of pixels.
Yep.
As opposed to.
I think
The best target if you wanted to trace waves is probably a polar region where the field is more or less radial, and you can place your slits along the direction you think the field is, and then you'll be able to trace waves along the slit, maybe, if that's what you're interested in.
Okay. Good
But
idea.
You have like a figure or something that shows like what the field of view or what the slits would look like on the sun to get an idea?
Yeah, I have to go to another presentation. Bear with me.
See what you want to know, Joe. 30 megameters. I suppose.
What's that?
It's around 30 megameters. So this is what, this one you want to know, right?
Yeah.
But this is basically 30 megameter. This is like,
So why is that in arc seconds? I mean, it's 0.75.
yeah, so
It's comparable. Let's just
instead of. Right.
You're going to talk about this later today.
Yeah, yeah.
yes, So.
Yeah.
So 30 arc seconds is pushing, it's pushing things a little bit.
Okay. All right, so that kind of answers one of my questions about how closely these need to be spaced.
But there were some, I know some proposals made to, for decus observations, I know John went over this, where people just talked about having us, because the cryo nurse has one slit, and they're saying about just letting it sit there. Maybe Richard is the PI on that.
that was, yeah.
Slit just stays there, and you see the waves sort of propagate through, so you can still learn something about waves, even with single
Yeah, okay.
fixed slits. So I imagine multiple fixed slits would also
Okay,
be possible. Is that true, Richard?
Yeah, the key thing from DCIS was the improved spatial resolution, though, and you might be resolving individual coronal structures with that, which is what I was more interested in that type of observation. And it seemed less likely to be able to do that with CORSAIR because the resolution is just a bit bigger. But you might see something interesting still. I just have to think about what.
okay. I like the idea also of aligning the slits with, for looking for waves in a polar region. We will have a roll stage in Antarctica, and we can make sure that, that we have enough range on that stage to sort of target a specific orientation as opposed to just freezing out the image roll. But this is what I think this is something like 60 slits. This might be like a 60 arc second spacing roughly. The squashing here is due to the grading anamorphic factor. So that's what the images look like. They need to be undistorted. And this is I think this is a PSI that I put the slits over just to have something that you could see. But that's kind of what it looks like kind of in maybe the worst case. We could do maybe a bit better than that if we at the 30 arc seconds, I think is a bit of maybe half that spacing.
Yeah.
That's kind of what you're asking.
And that roll angle is something you can like change like at will, or
Yeah,
is
in
it?
Antarctica, we're gonna have a roll stage, and so that's the question. We were originally designing our roll stage. This is why we're having this discussion. We were originally designing it to just take out the gondola motion and to freeze the field rotation, because it's an azimuth elevation mount, so there's field rotation. Freeze the field rotation for, up to an hour or two. But if we put more range on it, we can design it to point to an arbitrary angle. I mean, we wouldn't have to do a full 360, but we would do something, enough to get at least to either get a coronal hole or, Richard.
Do you have an idea of what the pointing stability might be for both instruments?
Yeah, we're so NASA Wallops has developed a gondola that points to about an arc second RMS over almost all time scales. So that's the the fast kind of half second time scale that we're taking exposures at, but also it stays that stable for around an hour. I mean, over a time scale of hours. And so the pointing stability is sub-pixel for us, or that's our goal. And NASA, they've taken that requirement and they don't seem to think they'll have a problem with that. So that's what we expect.
Okay.
The other thing is the Silicon 9 it'll be really interesting to see, because we can't do it with UCoMP, right? We don't have silicon line, but when we're finding for Cosmo,
Oh, yeah, you will, right? On Cosmo?
that's the plan.
Yeah.
And be able to-
10, we're talking about.
oh, so we're not talking about silicon line?
No, not 3.9 microns, 1.4
1.4,
to 3.
okay. Yeah,
But
this
if
is-
she gets amazing observations, it may impact
Yeah.
development on some level. I don't know. It
Yeah.
Would be hard.
It's really hard, yeah, because of how far into the thermal line
Yeah.
it is. So your instrument, you have different, but I mean, it's, yeah, I think.
What is it called, ETI right now? And all the 1.4
Yeah.
microns,
The timing might not be great for that.
or EIT rather.
But it's, okay, so you're gonna get silicon 10, 14, 30 with Cosmo. Is it,
We're working on it, but
Okay.
it looks like we can do it.
you can do it within gas, so,
We do with NGAS. NGAS is, it's the optical system is the
Yeah.
issue
Yeah.
and everything. But yeah, the camera is real happy at 1.4 microns.
yeah, it's probably happier than it is in the physical.
Absolutely.
Yeah. How important is it? When we were scoping CORSAIR for the proposal, there was sort of less interest until we added all these lines. And that turned out to be a real technical complexity for the test flight that, I mean, we just didn't have enough time to add all those mechanisms in. But is it a real disappointment? Like, do we want to add all those lines back for the Antarctic flight and take an extra year maybe to rebuild that into the instrument? How important is that? Momo wants like 1083 observation.
But more lights is better always. Well, depending on the eclipse or like next, I guess, year, because observations and the eclipse results, I think we're going on the feasibility of 1083.
Okay, yeah, so maybe that won't matter so much by the time we fly in Antarctica. Is it useful? So these observations would not be simultaneous. If we did add back the lines, we would have to refocus the whole instrument in order to target a new line. So that's only going to happen maybe once every hour or two. Is that still useful? What does UCoMP do? When it switches lines, it's
We
kind of
could
the same thing. Right?
Switch in a minute or two.
Okay, yeah.
So
Okay.
then there's flats and calibrations, depending what you're gonna do, but we could, the filter mechanism takes 40 seconds or something.
But do you switch back and forth rapidly, or do you observe for an hour or two?
Well, in the
and then
waves
switch?
program, we just sit and stare in the Iron 13, but in what we were calling the synoptic program, we've been taking 5 minutes in one wavelength, switch, and I think we're gonna probably, I think there's a discussion tomorrow about what we're gonna do, but it's very likely we're not gonna go 5 minutes, we're only gonna go 2 minutes before we switch,
Oh, so you-
because
okay.
all the CME people say that we don't get revisit enough.
Okay, all right.
Wavelengths, different thing.
So our,
Like, we have to we have to refocus the objective. We have
Yeah.
to move the filter wheel.
but,
The
that,
filter wheel
but
takes-
between pre-filters, it's, and
Takes a minute to rotate.
not a, the O1, but, it's not a full minute, but yeah. I mean, I could pull up the,
We're gonna talk about this tomorrow.
but
Okay.
I think we're gonna probably every 3 minutes switch to a different pre-filter going
Okay.
forward.
I think that would be challenging for us because when we refocus our objective, especially between 1 and 4 microns, it travels along like 80, travels a long distance. And I can't remember exactly how, I think 80 millimeters or something. And the gondola has to move a counterweight to keep themselves balanced. And their counterweight right now moves pretty slowly.
Sorry,
Yeah,
30 seconds to switch
30
filters.
seconds. Okay.
I mean, unless you choose the worst, longest or slowest.
Well, you've got a factor of 4 in wavelength of those.
Yeah,
Yeah.
that's
those
what's
lines.
so
That's
challenging.
huge,
So it's such,
especially if you have refracted optics.
yes.
I mean, in
Yeah.
the infrared, the dispersion of the refractive index flattens, maybe.
Not much.
But
Yeah.
the factor of 4 is huge.
Yeah, that's why we need to refocus. There was no way to design an achromat for the, at least not, I couldn't design an achromat for those.
Yeah.
We had to refocus. You don't have enough like lenses
Focus or
that
go to refractive optics.
reflective optics.
Reflective optics.
Well, so we thought about that, but you in particular said that you pointed out the advantage of having a lens as your objective instead of
Well,
a
it's the
mirror.
objective, but I
For
mean,
the- for the
also
others.
your other stuff.
Yeah, but the objective has to move the furthest. It's the one with the really long focal length, and so there's no getting around that. if
Yeah.
But yeah, we could
The
go to
dramatic
what?
focal, the change of focus,
The
it's a lot.
It's a lot, yeah, it's a lot. Yes. But we could redesign everything for reflective. That would be kind of a new instrument. But we can think about it.
You know?
Yeah.
Was the scatter, like, was the sky background, like the sky brightness at this level of the flight?
That's a good question. It's I think it's at 100,000 feet. It should be close to an eclipse. Like, I think you're above, I think it's dark up there. Maybe not an eclipse. I don't have a number for you, but it's dark. It's not like it is on the ground. It's significantly better. And I did look this up I think, yeah, at some point I had a number, but it should be much better. And then at 4 microns, the scattering is even better than at 1, just in general, because it's less efficient. So
But the instrumental scattering be higher, but it also gets better.
really, well, so what Pat was
It might be-
modeling was that the instrumental was better too.
Oh, it is
Oh,
better
okay,
more. I'm
okay.
saying the sky is probably going to be much smaller than instrumental scattering.
Oh, yeah, yes. The instrumental scattering, I think, is the dominant
Yeah.
one for us. Yeah,
Exactly.
yeah. There's not much atmosphere left to scatter.
Yeah. Yeah.
I think we've just been neglecting it, honestly, in our calculations, because the instrument and the thermal background at 4 microns is really bad. I mean, it can be if you don't do a good job cooling it. So that's the challenge there. But
Yeah, thermal stuff is,
yeah,
is a challenge.
yeah. See
And
about
then
that.
we have Tom Shannon help on that.
Yeah, he's
And
next,
the
right?
Deacon's content.
Yeah. Are there tools that would be useful to have for both? Are there sort of like general analysis tools? Are you guys gonna do any tomography, or are those tools useful to share with you? If we have them.
Tomography would be good. So you're saying,
So we're gonna observe, this is more of, this was Maxim's contribution, one of his contributions to the proposal, but it's because we can observe a solar rotation during the Antarctic flight, there was some reconstruction that he thought he could do with our 24/7 observations. And I don't know the details, and they hadn't been fleshed out because they were kind of out of the scope of that proposal, but I wonder if, I mean, UCoMP's observing all the time, although you have the day-night cycles, so I wonder if you would be interested in those as well.
we would love to have people working on tomographic construction of UCoMP, for instance.
Okay.
And, but I don't know if anyone's actively working on that right now. Maxime had worked on it and he got some UCoMP data, but I think when he's transferred over to work for DKIS,
Yeah,
he's kind of focused on other things.
I can see some real benefit to do that, just from the point of view of using your continuous data and seeing how well you do the demographic reconstructions and then comparing it to what we can do with comp with the limited time.
yeah,
And it's definitely relevant to the Qigong next generation with the coronagraphs, the idea of having a distributed network and the motivation for that.
oh, yeah,
Because
okay,
if you can demonstrate the importance of filling in those gaps or for getting the coronal magnetic field, basically.
I know someone in Argentina who is doing tomographic reconstructions for many instruments. Alberto Vasquez.
Yes, yeah.
Did he try this?
That's a good question. We should really collaborate with him. He's been involved in the whole heliosphere.
For a decade.
Yeah, he's been
But
doing
I
great
don't-
stuff.
I don't know that, and his colleague there as well.
Yes,
Fernando. I don't know, but they requested some UCoMP data, but I don't know that they've had time to really.
Rich David at Michigan.
and of course, Richard, yeah, we should reach out to Alberto because they're very good and
UCoMP tomography will be more challenging because you only have a limited data set each day. And I think Shanyu has done some tests to try tomography for both intensity and magnetic field. But the results are not very good because the resolution, the temporal resolution is really bad. So
Alberto and Diego Llaveras were at our meeting, our data meeting, remember? They were involved. We need to reach out to them. It is true, but but that's why having this as a kind of a, to sort of see what you gain by the addition. That'd be really interesting.
I've got some interesting results with comp data back in the day. So it,
For in testing.
For linear polarization and
linear
Yeah.
polarization to
Because you still have a continuous observation for linear polarization, even within 4 or 5 hours. I think, yeah, but when Xianyu tried that, because he's using the magnetogram from wave observations, you only have one map each day, so.
yeah, you wouldn't be able to do it.
That's why.
That's a question. There are some days where we could run. This is for tomorrow. Yeah. We have a month that you dedicate to tomography and you're running waves. Well, or I mean, or what you could do is you could use the linear polarization and the intensity and then like scale your field based on your daily magnetic field, right? Because it kind of gives you a magnitude on some level. If you could, I'm just kind of speculating here, but taking the kind of thing Maxim was doing with linear polarization and then using like as a kind of a ground truth strength on it from the waves each day. I don't know.
yeah, Maxim used one image per day. I mean, one kind of coverage image per day.
Per day?
Yeah, and but you need like 30 of them, right? Over a month. And that's how to get the topographic.
I had a question for Alan, actually, because at some point you mentioned that there are other ways besides tomography to do the, like, to try to remove the line of sight effects. And I was wondering if you have, like, I don't know, particular interest in what would you do with this data, or what would be interesting? Or if I'm misremembering, feel free to just.
CLEDD can embed vector magnetic fields from such data directly on the spot without tomography.
Without what?
Without tomography.
Okay,
And you have a line of sight component attached to the inversion because otherwise the inversion would be ill-defined. So.
so what do you need for this? What, I mean,
Looks like
what
UV.
observations?
In two wavelengths, 10
Two wavelengths.
So it looks like UV in 2 wavelengths, but you need,
Or a wave program and some more complicated stuff.
so then that would either indicate that we would have to put, if we can measure Stokes speed, we'd have to put back the ion line or
But with just one line, you still get the line of sight magnetic field.
Okay,
That's still doable.
oh, you don't get the vector.
You don't get the full vector. Well, you do get it, but it's hard to interpret.
All right, so then that's something else to maybe we could talk about.
Janet?
Yeah.
I have, I'm curious, what kind of maximum height you would expect you can detect silicon-9? Because it forms at around 1 million Kelvin, like iron 10. I think for the red line, we actually don't observe them at a very large height above length.
Yeah, that is, I don't have the intensity here, but I think it's definitely concentrated lower down in the corona. I don't have a real max for you, but I think
Okay.
certainly for Stokes B, we probably can't get good measurements of Stokes B kind of much above maybe 1.2 or 1.3 above the limb. The culture here is at 1.05, so yeah. But the nice thing compared to iron 13, which I think I got rid of because we're no longer measuring it, but I think it's hidden behind here. Like the iron 13, you don't see as much at the poles, but the, you know, the lower temperature, you
Yeah.
kind of get coverage around the whole corona.
Yeah, the temperature is nice for silicon nine.
Yeah, it's different enough.
Yeah, to have a lower temperature for solar minimum observations.
Okay.
A lot of reasons to source that.
How does UCoMP, you mentioned this the first day, but I've forgotten what your, how often do you produce an IQ UV, like, before you sum them?
We've, in the waves program, we produce a data product every 31 seconds.
Okay.
it would be more efficient the way we built it to make that like 36. We're losing more overhead to tuning the filter, but we go through enough of all the things to get a full, yeah. So there's a FITS file with the dynamics of polarization every 31 seconds or so.
Okay,
So our liquid crystal that in our modulator is really fast. And so we go through, you know, 4 modulation states
We're switching that at 90.
really fast.
3
And then
milliseconds.
we take another 4 and we do that 16 times and we sum all of the ice. Well, it's not IQ. There were 1, 2, 3.
Okay.
In the modulation state, we sum those all at the same wavelength, and we change the wavelength, which takes 300 milliseconds. And then we do that again really fast, almost continuously with the fast modulator.
you sum your modulated intensity before converting?
Yes.
Okay,
We before we do anything else, we sum that. I mean, then that's causing us some problems, so we might want to add in some sort of filtering there
Mhm.
for when the jitter is bad and the other stuff. But
Okay.
Right now it's just as soon as we're collecting, you know, we never write out an
oh, this
raw
was.
image.
Yeah,
We're only writing out a sound. I mean, it has a mode to write out a raw image, but the bandwidth things less than 1% of the data out there was anything but some 14 or 16 times before writing out.
That's right, you talked about this the first day, about your advantage. Okay.
3 more minutes.
Yeah, I think
We
I'm,
go on break in 3 minutes, so.
yeah, any other comments? before we-
Oh, yeah.
That's a good question. I think, so for the test flight, this is just gonna be on the ground. The test flight is only 8 hours and, it's an additional complexity to add calibration optics. So we'll do it, I think, before and after. And I think it's sort of an open question because we're above the atmosphere. I hope that timing isn't as important because we don't have the kind of the lensing effects of the seeing. So maybe we can get away with doing it kind of in the lab before and after, but maybe we should do it on the ground before and after, right at the site. I think in Antarctica, I guess this is a kind of an important consideration that I don't think we've fully resolved yet. I was interested to notice that COMP does it once a day or something like that. UCoMP, sorry.
Polarimetric calibration. we do
Yeah.
it Once a day on UComp. That was, for comp, we didn't, we had
What did you
to,
do for?
for comp, we did it once.
3-4 times ever.
Oh, okay. That's what I was kind of
And that
intending
wasn't
to do,
good.
and then I said, oh.
That wasn't sufficient.
All right.
So we haven't done a really great analysis about how much our polarimetric calibration changes. KCOR, we know we need to do it every day.
Yeah.
So, and then we have done it every day, but for the last few months of operations, we didn't do it every day. We were doing it more like once a week
On COMP.
on UComp.
And did it affect your measurements? Could you tell that things were not?
Steve has to manually process the polarimetric calibration, so we've only used maybe twice. We've changed it through the whole mission, so we're not.
Oh, so all those,
There's
the
a
data
few-
that you were showing was with kind of 1 or 2 calibrations.
Which for comp,
Yeah, all the UComp data is on 1 or 2 polarimetric calibrations. We don't, the Mike's pipeline doesn't do polarimetric calibrations.
oh, I know.
Yeah.
I understand that. I do polarimetric calibrations. Can I tell you how it's done? Early in the mission for UComp, we noticed that there was a temperature dependence of the calibration. So, but we have a temperature sensor on the polarimeter. But we also, so we have, so I was able to determine the demodulation matrix as a function of temperature. And I give that to Mike, and that's what Mike uses. It's the same, and it's an average of all of the data we take, taking into account the temperature dependence.
Okay.
In addition, we added a temperature control of the modulator.
Yeah.
So we actually have a closed loop that is maintaining the modulator temperature
Yeah.
really well. Even though we have that temperature calibration of the demodulation, we also stabilize the temperature of the modulator, which helps.
So-
So you can do it either way, and we're kind of doing both.
Mhm.
You know,
I think your biggest impact to calibration is the temperature and maybe the C. Are those the two big ones? Do you have a? So I wanted to talk to you a little bit about this tomorrow, just about
Yeah.
Corsair anyway, but we can.
yeah, I mean, they're different, right? I mean, the seeing is doing like random things, whereas the temperature of the modulator would do a systematic.
So you can, that's why you can model it out or get rid of it.
Yeah,
Kind of with your
and we
temperature
have,
measurement,
you know,
yeah.
we've done that. So, like I said, yeah, it's always good to have temperature sensors on
Yeah, okay,
critical items so you can back things out, after the fact.
Yeah.
So that will, I mean, obviously for Corsair, that would be a good thing to do.
yeah. Although we're less
If you,
sensitive.
you know, are gonna calibrate it in the lab, then to make it be valid through the flight, I
Yes.
think.
Yeah, on the wave plate, yeah.
Yeah.
Okay. That makes sense.
I have a question for you, Steve. You said you were averaging over the temperatures. Was there a way to compute sort of the standard deviation and the demodulation matrix elements from that process? So we have a range.
We have that.
Yeah.
I don't have it in my head.
No, but I'd
But,
like
um,
to see that too.
We have all that, yeah.
Yes, you can almost run it at the extreme and then just see what the difference is.
Yeah,
You
how
put it
how
in-
far off you are. Yeah,
Exactly.
from
I'd
true.
like to see that myself, actually.
Yeah. It gives you an idea of your error bars on those measurements.
Exactly.
The systematic error bars.
Yes, exactly.
But we were taking calibrations every day, which is a huge improvement over comp. So you come and, you know, they're very consistent. You know, we end up using the average of hundreds of calibrations. So it lowers the random errors on the demodulation matrix elements by doing all that averaging. And I think the biggest component of the systematic error is the temperature. And we're also, you know, beating that down by measuring the temperature and backing that out, and also trying to maintain the temperature, constant temperature. So it's pretty good. We can show some people are interested. Well, go ahead, Tom.
Good morning, everybody. Hi, Steve. Just a quick question on that. I think I've noticed in the headers that there's a demodulation matrix or calibration matrix in the headers for the L1 data. Do you only apply one matrix to the whole field, or is there any field dependencies?
Right now, we apply one to the whole field. But we measure over the field. So if we decided we wanted to change that, I think we could then fit it across the field and apply that to. That's something we could upgrade to. We have and apply it going backward.
Do you
But at
see
the
much
moment, it's just a constant, we assume a constant matrix across the field.
Yeah.
do you see much changes?
What's that?
Do you see a significant change at all across the field in the data you
People
have?
start complaining to me that there's a problem. I'll change it.
Yeah.
But, at the moment, I haven't seen any compelling evidence or heard from any users that they think it's an issue.
Okay.
Were you gonna say something?
I'm gonna work with Mike and we'll get the extrema. And I'd like to just run that.
Mike doesn't have the extreme.
Okay, well,
Mike has a
we'll-
file that I get.
We'll work with you to get some.
The matrix coefficients and the temperature
Yeah,
coefficient
because Mike only has like.
for them, so,
85,000 things to do.
Mike doesn't have. Mike's not gonna be able to help you.
They'll come to you first.
Yeah, that's a good idea.
Yeah, because Keiko does have it by pixel, the demodulation.
So why don't we break now? And Tom, you're gonna be up after the break, I think.
Sounds good.
And at 10:10, we're gonna have an exciting